Professor.
Hey Nicholas, how's it going?
Good, how are you?
Good, good.
That's good. Uh, Next week or next Wednesday, right?
Yep, next Wednesday. Yep, one more week.
It's gonna be stressful. Sucks is tomorrow I have to go in and talk to one of my managers that deals with the scheduling,
Mm-hmm.
and so pretty much like they didn't ask me and nor did my availability change, and so they're having me like come in on a not this Saturday but next Saturday like in the morning, but I
Oh
can't
man.
do that.
Oh dang.
It sucks because like they didn't because like originally they asked me to like for this Saturday to cover like a morning shift,
Yeah.
and I said yeah I can do that, but after that I was assured that it was just gonna be like one time thing.
Mm.
Yeah, so it's gonna be fun.
Well, best of luck.
Yeah, well I don't know, I just got to make sure I'm assertive and don't give them an inch and they'll take a mile type of thing.
Right, right, right.
What are the topics we're covering today?
So the results of the poll were just all radiation stuff, and so we're going to go over radiation exchange, and then radiation concepts. So, like the conceptual stuff around radiation. Okay, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. Good afternoon for the last time. So how's everyone doing today? Good. Good to hear it. Yeah, long week, long semester, right? And so we're finally at the end. And so today, we're having a special class session. And so Monday, we finished up all the content that I had planned for the class. And so today, we're just going to be reviewing for the final, okay? And so right before the class, I looked at the poll, and the two leading topics were just all the radiation stuff. And so the first most requested topic was radiation exchange. And so for that, I thought I'd help you guys walk through the homework problem, okay? Or at least, we'll do problem 3, and then I'll show you how to set up problem 4, okay? I think that would be good practice for radiation exchange. And then the other topic that everyone wanted to see was radiation concepts. So a lot of the conceptual stuff with radiation. And so for that, what I thought I'd do is I'd look at the study guide for the final, and I'd go through, what I think are probably the most important learning objectives, and I would tell you, and I'll tell you how I would answer those if it was me on the exam, okay? All right, so before we start, there's one announcement that I have to make, is that we haven't talked about this yet, but SOQs are up for this class, okay? Okay, and so those are your student opinion questionnaires, right? And so, please go fill those out. And so, I consider them to be course evaluations. That's kind of what I've known them to be, before I started working here. Those are extremely important because, that's kind of your guys' chance to really kind of give me feedback on how the class went for you. Okay. And so, this is a required class. And so, everyone is required to take this class. And so, because of that, because it's part of our core curriculum, we really want to hear from you guys to try to make this class the best that it can be. Okay. And the best way that you can do that is through the SOQs, because, I mean, you guys know at this point, but the SOQs, it gives you a list of, questions where you can rate, on a scale of, 1 to 5, things like that, and then ask you for the comments afterwards, right? And so if you guys go fill that out, and give your feedback, not only on the numerical stuff, but, just also with your comments, that would be really, really helpful, okay? Because for me, it's been a couple of years since I've taught this class. And so this was actually, I taught this class on my very first semester that I started working here. And this is only my second time teaching it since then. And so, I know a lot of things were kind of rusty and not everything worked out super well. And so, I want to hear from you guys about, the things that worked well, things that didn't work well, so that I can improve for the future. Okay. And just in general, not only for this class, but for all your classes, it's really important to fill these out, because generally what tends to happen is that trends and tools evolve kind of in the professional engineering space a little bit faster than what we can keep up with here in the classroom. And so hearing feedback from you guys and how things went, that allows us to kind of reshape and kind of retool our classes to be more beneficial for the future and make things, kind of more effective for everyone, okay? And so that's, all that is extremely important for the class and just, for the curriculum in general. And so, definitely go fill those out, right? And if you had a bad experience in the class, you can definitely vent it all out on the SOQs too. So, I've had people curse me out on the SOQs, and I think that's good, right? Better that than than kind of penting up all those emotions forever, right? And so, SOQs are completely anonymous, so feel free just to be honest, right? So honesty is always the most important things, when you're giving these kind of feedback. So please go fill it out. Please be honest, and don't hold back anything for this, okay? All right, and so let's remind ourselves again when the final is. Okay. Okay, and so the final exam is going to be exactly 1 week from today. Okay, and so it's going to be on Wednesday, May 19th. Okay, and it's a 2-hour exam, and I always forget what the time is for the exam. And so let's look at it again. Okay, the exam is going to be from 3 p.m. to 5 p.m. Okay. right? And so it's going to take place virtually, and so it's going to take place, you know, over Canvas, just like all our midterms, okay? And it's going to be a little bit longer than our midterm exams, just because the time that you have for it is a little bit longer, okay? And so instead of an hour and a half, what you have here is 2 hours. And so, you know, I've added one question each to the conceptual part and also one question for the problem solving part, okay? And so, you know, I haven't written the exam yet, but typically, you know, for the final exam, I tend to make those questions a little bit easier than the midterm exam questions. And so, you know, it's more kind of a question, you know, the final exam is kind of more a question of, you know, how well did you kind of absorb everything from the class, okay? So a little bit less on the details and kind of more on that. Because I know for the final exam, there's a lot to study for. And so, you know, I try not to go too much in depth, you know, partially due to the time constraints as well, okay? All right, so are there any questions before we start our midterm review or final review, sorry? Okay, all right, so let's go ahead and get started, okay? And the first topic that I think most people wanted to see from the survey was radiation exchange. All right, and so this was kind of the last radiation topic that we really went over, okay? And so, you know, I'll tell you right now that the problem solving question on the exam regarding radiation will be something along this vein, okay? So it'll be kind of a radiation exchange problem, right? And so to kind of help you guys out with that, I thought what I'd do is let's do problem 3 on the homework, and then I'll start problem 4 a little bit just so that you kind of get a sense for the setup, okay? So this is homework 7, problem 3, okay? Okay, and so in this problem, you know, what we have is kind of a, what I like to call like a radiation fin, okay? And so what we have is kind of this sawtooth pattern like this, okay? Or you can say it looks like Charlie Brown's shirt, so, you know, either one's fine, right? And so these lengths right here, this is 10 centimeters, okay? So both of those are identical. And then this gap right here will be 5 centimeters, okay? And then what I'm saying is that this, these jagged things right here, they're all at the same temperature, and that temperature is 350 Kelvin, okay? Right? And then outside this fin, you know, in this kind of this region up here, what we have is what I call deep space. Okay, and deep space is at a temperature, we'll assume just for this problem, we'll assume it's at a temperature of 0 degrees Kelvin. Okay. All right, and so throughout this problem, you know, there's several parts of this, but eventually, you know, we want to solve for things like, you know, what's the heat loss to deep space, you know, and a bunch of other stuff. Okay. All right. And so to tackle this problem, you know, what we're going to do is we're going to kind of tackle this kind of one, you know, just one enclosure from one enclosure, and then kind of extend those results to, you know, to the other stuff. Okay. And so let's look at just this, just one system here. Okay. And so I'm going to go ahead and extract this just like this. Okay. Where this length right here, this is 10 centimeters. This length right here is 10 centimeters, okay? And this opening right here is 5, okay? Right? And so typically with these radiation problems, radiation exchange problems, we like to work within a confined space, okay? And so here we don't really have a confined space because one of them is open up to deep space, okay? But to kind of simplify it, what we can do is we can kind of draw a pseudo surface, or like a, you know, a boundary here. Okay. And so if we draw a line across that enclosure right there, so now what we have is this triangle, and now what we have is an enclosed space. Okay. Right. And so an enclosed space is nice because from this, you know, we can apply things like we can compute the view factors a lot more easily. We can form our thermal circuit for this, right? And so it's going to make this things a lot easier, right? And so when you're doing these kinds of radiation exchange problems and you're trying to look for and you're trying to kind of form an enclosed space like this, or a closed system, don't be afraid to kind of draw these kind of pseudo surfaces so that you can kind of close your area. Okay. All right. And so now what we have is we kind of have this 3-surface system. Okay. And so I'm going to go ahead and label these surfaces. And so I'll call this one right here surface 1. Call this one surface 2. And I'll call this opening here surface 3. Okay. All right. And then from here going forward, we're going to assume that we have this 3-surface system, and we're going to compute the view factors and the radiation exchanges and all that stuff. Okay. All right. So any questions so far on the problem setup? Okay. All right. And so before we move on, let me do this too, actually, because this will kind of set us up a little bit easier for problem 4 too. Right? And so it's not required for this problem, but I think it's really helpful to draw the thermal circuit for this radiation exchange. Okay. All right, and so for the radiation exchange circuit, one thing I forgot to mention is that for this problem, we're assuming everything, we're assuming all surfaces are black bodies. Okay. Okay. And so what black bodies means is that their emissivity is going to be equal to 1. Okay. All right. And so what that means is that, we're not going to have any gray body resistance here. And so the only resistances that we're going to have are just strictly from the view factors. Right? And so if we go ahead and label these circuit nodes, okay, so we'll call this node 1, we'll call this node 3, and we'll call this node 2. Okay. We need to draw a resistor that connects each of these nodes to each other. Okay. Right. And so for a 3-node system, it looks something like this, right? And so we have kind of a triangle of our resistances. Okay. Where this resistance right here, we'll call this R13. Okay. This represents the heat transfer that goes from surface 1 out into deep space. Okay. And so this can be A1, F13 raised to the -1 power. Okay. This resistance on the bottom here will be R12, and so this is the resistance, or this represents the radiation heat transfer between surface 1 and surface 2. Okay. Okay, and that resistance is equal to 1 over A1 times F12. Okay. Okay. And finally, we have R23, which represents the heat transfer, radiation heat transfer from surface 2 out into deep space. Okay, and so this is going to be A2 F23 raised to the -1. Okay, all right. And so it would be really nice if we can compute all of these resistances here. Okay, and so to do that, we need to compute all the view factors. Okay. And that's exactly what part A of the problem asks you to do. So for part A, what that part asks you to do is to compute all the view factors in this problem. Okay. Oops. All right. And so usually where you have to start out with this is you have to start out with some kind of equation. Okay. All right. And so, this kind of triangle enclosure that we have here on this page, this matches up perfectly with a situation from table 12.2. Okay. Okay. And the situation is called a 3-sided enclosure. Okay. And so for a 3-sided enclosure, what we have is Fij. Okay. And so in other words, the view factor between surfaces I and J is equal to Wi plus Wj minus Wk, all divided by 2 Wi. Okay. Where each of the W's here, each of the W's is the length of the surface. Right. And so in this case, since all of our surfaces belong to this three-sided enclosure, we can actually use this formula to compute all the view factors in our system. Okay. Right. But just for just for a demonstration's sake, because a lot of times this isn't true all the time, what I'll do is I'll use this to compute one of the view factors, and then I'll compute all the other ones using our view factor rules, right? And so our reciprocal rule as well as our summation rule. Okay. All right. So any questions on this so far? Okay. All right, and so let's go ahead and use this equation to compute F12. Okay, and so F12, okay, we need to plug in for Wi, Wj, and Wk, okay? Right, and so Wi in this case is gonna be the 10 centimeters, okay? Wj, which is the other surface that takes place in this view factor, right? And so Wj here is going to be 10 centimeters. Okay. Okay. And Wk, so Wk is the interesting one because it's the length of the surface that doesn't take part in this view factor. Okay. And so here Wk is going to be W3, okay, which is just going to be 5 centimeters. Okay. All right, so let's go ahead and plug all that in. And so F12 is going to be Wi plus Wj minus Wk, all divided by 2 times Wi. Okay. Okay. And so up top you have 10 plus 10, which is 20, minus 5, which is 15. And on the bottom, what you have is 2 times 10, which is 20. And so you have 15 divided by 20. And so this first view factor here is 0.75. Right? Okay. And so let's use this view factor to compute all of the other ones. Okay. All right, question. So why do I subtract 5? And so I subtracted 5 because that's what Wk is. And so if we go back to the previous formula, we have Wi plus Wj minus Wk. And so in this case, Wk is the third surface. Yeah, and so third surface here has a length of 5. Mm-hmm. Yep. Okay. And so now let's use this F12 to compute F21. Okay. Right, and so in particular, let's use the reciprocal rule, okay? And so you don't have to do this, and so you can actually use the exact same formula up here to compute F21, right? But I just want to show you that once you have one like this, then you can compute the reciprocal one, okay? Because F21 here is kind of like the partner for F12, right? And so what we know from the reciprocal rule is that F21 is equal to F12 multiplied by the ratio of their areas. Okay? So we have A1 divided by A2. All right. And so since surface 1 and surface 2 here are identical, then their ratio is just going to be 1. Okay? Right. What we get is F21 is equal to F12. Okay. And so F21 is equal to 0.75 as well. Okay. Right. And so that's good. Okay. All right? And so now we can just, find all the other view factors using these rules. Okay. All right. And so before I start applying the summation rule, let's compute the self view factors. Okay. And so the self view factors, remember, are going to be the view factors of the surfaces with themselves. Okay. And so for these, we have F11, F22, and F33. Okay. Right. And these, remember, represent the fact or represent the potential for these surfaces to radiate on itself. Okay. And remember, this can only happen if your surface is concave, because if it's concave, then you can stand on the surface and view another part of the surface. But since all of these guys are flat surfaces, then there's no way for this to happen. And so all of these self view factors here are going to be 0. Okay, and the reason is all surfaces are flat. Okay. All right, and so now that we have these guys, we can use the summation rules to compute the view factors between these surfaces and surface 3. Okay. So any questions on this? Okay. Okay, and so let's go ahead and use the summation rule to find the other view factors. All right. And so let's start with F13. Okay. From the summation rule, we know that F13 is equal to 1 minus F11 minus F12, right? Because what our summation rule says that all of these guys should add up to 1, right? And so since we have 3 surfaces and they're all in an enclosure, we know that all of their view factors should add up to 1. Okay? And so if we solve this equation for F13, this is what we get. Okay, so if F13 is equal to 1 minus F11, we know this guy is 0, right? Because our surface is flat. Okay, and so F12 here, we just computed on the previous page, is 0.75, right? And so F13 here is simply 0.25. Okay. We can do the exact same thing for F23. Okay. And so F23 here is going to be 1 minus F22 minus F21. Okay. Right. And so we can plug in for all of our known view factors here. So F22 is going to be 0. F21 is going to be 0.75, right? And so in the same way like before, F23 is going to be 0.25, okay? All right. Okay, so we're almost done. And so we just have 2 more view factors we need to find. And the way that we can find them is with the reciprocal rule. Okay. Okay. All right, so let's start with F31. Okay, so we know F31 is equal to the ratio of A1 divided by A2, or A3, sorry, times F13, okay? And so this ratio right here, let's go back and look at our triangle. We know that surface 1 is twice as long as surface 3, okay? And if we consider, that this fin goes into the page like this, right? Right? And we assume that this length is the same for all of them, right? And so the length into the page is basically the same, okay? Then what we know is that the area for surface 1 is going to be twice the area of surface 3. Okay? Just simply because it has that dimension that's twice as long, okay? And so if we use this fact, we can say that this ratio of A1 over A3 is going to be 2, okay? And so if we plug that in, we can say that F31 is equal to 2 times F13, okay? F13 we just computed up here. And so this tells us that F31 is equal to 0.5, okay? And then we can do the same thing for F32, okay? So F32 is going to be A2 divided by A3 times F23, okay? Where again, this ratio right here of A2 over A3 is going to be 2, okay? And so this tells us that F32 is also 0.5. Okay. All right. And so that's all the view factors. And so now we can plug these things in to our circuit and compute all the resistances. Okay. All right. So any questions? Any questions on this?
Can you explain why you multiply A1 over A3 by F13?
Yeah. So this is our reciprocal rule. And so this tells us is that, what this tells us is that if we have, let's say F31, right? We can set this equal to the reciprocal view factor, where the reciprocal view factor is just kind of the same view factor, but the two indices are reversed, right? And so we say is F31 is equal to F13, but we also have to multiply these by an area. And so for F31, we have to multiply by A3, and F13, we have to multiply by A1, right? And so the area that you multiply kind of has to match the same index as kind of the starting one for that. And so all I did was I took this relationship and I solved it for F31. And so I divided both sides by A3. Okay, so that's going to cancel out on here. And on the right-hand side, we have A1 over A3 times F13. Yeah. Mm-hmm. Right. All right. Any other questions on this before we move on? Okay. All right, and so that's part A of the problem. And so part A, I asked you to solve for all the view factors, okay? Part B, we want to solve for the amount of heat loss to deep space. Okay, and so for this, I'm going to return back to the circuit. Okay. Right, and so if we consider the fact that deep space is node number 3 right here, okay, the amount of heat loss to deep space here is going to be the combination of the heat flow over this resistor right here, okay, and this resistor right here, okay. And so what we want to compute is Q13 as well as Q23, okay. All right. And so let's go ahead and compute that from the circuit. Okay? And so, usually from our circuits, what we always do is that if we want to compute the heat transfer over a resistor, what we do is we take the difference in between the nodal values and then we divide it by the resistance in between, okay? And so let me go ahead and label all of the nodal values here because, we assume that everything here is a black body, okay? And so for node 1, our nodal value here is going to be sigma T1 to the 4th, okay? Okay. And so for node number 2, we have sigma T2 to the 4th. And then for node 3, what we have is sigma T3 to the 4th, okay? All right, and so let's first quantify this, this heat transfer right here, Q13. All right, so we have Q13. This is going to be equal to the change in the nodal values, okay, divided by resistance between them. Okay. And so if we write this out, so the difference in the nodal values will be sigma T1 to the 4th minus sigma T3 to the fourth, okay? And then the resistance in between them is going to be R13, okay? Right, and so everything here we know, right? So we know sigma. It should just be sigma, not sigma 1, okay? We know the temperatures because those are given to us in the problem, okay? And we can compute R13 because this is just comprised of the area multiplied by the view factor, right? All right, and so Q13 here is going to be equal to sigma times T1 to the fourth minus T3 to the fourth, okay? For this problem, we're saying that the temperature of the deep space is 0, and so we can just plug in 0 for that, okay? And then we're going to divide by the resistance in between. And so the resistance in between is going to be A1, F13, okay? Right? And so what we get in the end, if we simplify this, is A1, F13, sigma, T1 to the fourth, okay? All right. And so here we can just simply plug everything in, okay? Because we know the area, and so the area, you know, in this case, it's just going to be the 10 centimeters, okay, which is equal to 0.1 meters, okay. And then we're going to multiply this by the depth into the page. And so I think in this problem, what I tell you is to solve for this per unit length. And so what you can do is you can just assume that the length is 1, okay. F13 we solve for, and so F13 from here, we know F13 is 0.25, right? Sigma is just a constant, and so sigma, remember, is 5.67 times 10 to the 8, or minus 8, okay? And then T1, of course, here is 350 Kelvin, okay, from the very beginning. All right, and so if we solve for this, what we get is a value of 21.57 watts, okay? And since we're solving it per meter, we can say this is 21.57 watts per meter, okay? And so, you know, that's the first part of this. And so the other part is we have to solve for Q23, okay? And so this is gonna be sigma T2 to the fourth minus sigma T3 to the fourth divided by R23. Okay. And so R23, you know, we know is, you know, we can compute that from the shape, from the view factors, okay? And so in fact, you know, you plug everything in here, you find out that this is, you know, identical to Q13, right? Right, and so if you plug in all the numbers, you'll see that Q23 is also equal to 21.57, okay? And so overall, the overall heat transfer is just going to be the sum of these two guys. Okay. And so if you add their values together, what you get is 42.54 watts per meter. Okay. All right. So any questions on this? Okay. All right, and so that's part B of the problem. Okay, and so next part C, I asked you to do something kind of interesting. And so part C, what I asked you is, you know, let's say that we don't have any fins here at all. Okay. Oh, question. 4. Oh, okay. Yes. Okay. And so let's say that we have a situation where we have no fins. Okay. And so instead of kind of our Charlie Brown shirt that we have for our surface, what we have instead is kind of a flat patch like this. Okay. Right. And so we kind of just smooth the whole thing out. Right? And so let's say that, you know, we'll consider a patch that takes up the same amount of horizontal space. Okay. And so let's say that we'll consider a patch that is 5 centimeters. Okay. And so let's compute the radiation exchange between this and deep space. Okay? All right. And so in here, you know, we have kind of a much simpler case because we just have kind of two surfaces or two places, okay? And so we just have to draw one resistor in between, okay? Okay. Okay. But in this case, you know, because we just have one surface, this F13 here is just going to be 1, okay? Because what we can say is that, you know, because there's no other surfaces here that kind of impede it, then every single radiation ray that comes off this surface is going to go into deep space. Okay, and so what we can say is that, you know, since all the radiation from this surface goes to deep space, the view factor is just going to be simply 1. Okay, all right. And so the heat transfer here is going to be sigma T surface to the 4th, okay, minus sigma T space to the 4th, okay, divided by A1, okay, times F13, where F13 here is just 1, and so we can kind of just ignore this, pretend that's not there, okay. All right. And so if you plug in the numbers for this, then what you actually get here is 42.54 watts. Watts per meter. Okay. All right. And so if you check this solution against what we got from before, you'll see that they're exactly the same, right? And so that's kind of depressing, right? And so in part D, you know, what I asked you to compute was the effectiveness. Okay. And so the effectiveness for a fin is simply going to be, if you remember kind of way back when we did fins before, it's going to be the heat transfer from the situation with the fin compared to the situation without the fin, okay? And so if we compute this ratio, you have 42.54 divided by 42.54. What you get is an effectiveness of 1, okay? And so what that tells you is that you gain absolutely no benefit at all to making this fin, right? And so you did all that work to kind of make this sawtooth pattern on your satellite or whatever, and it did absolutely nothing. And so, you know, you kind of wasted your time and wasted your engineering budget on that, okay? And so it's a little bit depressing, right? But you know, there's a very good reason for this, and it kind of boils down to one kind of key assumption that we made at the very beginning. Okay, so are there any questions on this? Okay. All right, and so why do we get this? And so why did we get this very depressing result? Okay, and so that's kind of what I asked you in part E. And so in part E, you know, what I asked you is that, you know, we did all this work to do this fin. Why don't we see any kind of improvement? Okay, and the reason we don't see any improvement has to do with the fact that, you know, we assumed everything here was a whack body. Okay. And so because of that, you know, what tends to happen is that, you know, you're making this fin, and so you're kind of taking the surface, and you can kind of imagine you're kind of taking it and kind of depressing it like that, okay? And so even though you're increasing the overall surface area of your part, okay? Okay. What's happening is that, you know, as you're increasing the surface area, you're also increasing the potential for the two surfaces to radiate each other. Okay. Right. And so let's look at our view factors again. And so let's kind of see what this means. Okay. Right. And so the key view factor here is going to be F12, right? So F12 is 0.75. Okay. And so what does that tell us? And so if we go back to our initial kind of geometry here, if F12 is equal to 0.75, that means 75% of the radiation that's coming off this surface is just going straight to surface 2, right? And so that doesn't help us, right? Because what we want is we want to offload this heat into deep space, okay? But if 75% of our radiation is just going right back to our device, then that doesn't help us at all, right? And so, in this case, because we assumed it was a black body, and that kind of, makes it so that, your radiation can't reflect, right? And so remember, for a black body, whatever radiation hits it, it's going to absorb, right? And so because we have 75% of the radiation that's coming off here just being reabsorbed by the same surface, you're not really getting any benefit from having the fin, okay? And so it's kind of a an interesting problem here. Maybe kind of a depressing and kind of disappointing result, but I think it's kind of nice for kind of running through this entire process of radiation exchange. Okay, and so for this, I tried to go kind of really kind of step by step here to kind of illustrate that whole process for you guys. Okay. All right. So any questions on this before we move on to problem 4? Okay. All right. And so I'm not going to work out all of problem 4 for you because I think that would take up the entire class period, but I will show you how to set it up. Okay. All right. And so problem 4 is you're working with the same geometry. Okay. Same geometry as problem 3, except the only thing now is we're going to relax our assumption of the black bodies. Okay. Okay, and so in fact, I think I tell you that the emissivities here are going to be 0.85. Okay. All right. And so primarily what this is going to do is it's going to affect your thermal circuits, and it's going to make it so that you have to add in the effect of the gray body resistance. Okay. Okay. All right, and so let me draw the circuit for you. The updated circuit, and then we'll talk about how you have to go about solving this problem. Okay. All right. So first, actually, let me start with the same circuit that we had before. Okay. Okay. And so this was our original circuit, right? And so we had each of the view factor resistances in between each of the different surfaces, right? And so we had R12 for the resistance between surface 1 and surface 2, R23, and R13, okay? And so previously what we had was that, for each of these nodes right here, what we had was their black body emission, right? And so for here we had sigma T1 to the 4th. Here we have sigma T2 to the 4th. Here we have sigma T3 to the 4th, okay? Okay. And so when you have gray surfaces, you can no longer assume these to be the nodal values, okay? Okay. And so instead, what we have here, for this kind of inner circuit right here, we have to replace these with the radiosities. Okay. And so here we're going to replace it by J1, J2, and J3. Remember, J here is radiosity. Okay. Right. And the way that we get the radiosities, or the reason why we have that, is because we have this gray body resistance. Okay. And so from the inner circuit, what you should do is you should draw an additional resistance that goes out. Okay. Okay. And each of these resistances here, these are going to be your gray body resistances. Okay. So first we have R1, which is just the gray body resistance for surface 1. We have R2, which is the gray body resistance for surface 2. And we have R3, which is the gray body resistance for surface 3. Okay. Right. And the gray body resistance, the way that you compute it is you take your emissivity, you do 1 minus emissivity, and you divide it by emissivity times the area. Okay. Right. So R12 here is going to be 1 minus epsilon 2 divided by epsilon 2 times A2. Okay. And R3 here is going to be 1 minus epsilon 3 divided by epsilon 3 A3. Okay. Okay. And so when you start to have gray body resistances, or when the emissivities are less than 1, this is what you need to do to adjust your circuit. Okay. Right. And then, of course, at the very ends of the circuit, that's where you would put the black body emissions. Okay. And so at the very ends of this, at the very tips of the circuits, you have sigma T1 to the 4th, sigma T2 to the 4th, and sigma T infinity to the 4th. Okay. All right. Okay. And so that's kind of the most general circuit that you can have. Okay. But in this problem, what I think one more thing I told you was that you can assume that deep space here is still a black body. Okay. Okay. And so remember, deep space is our node 3. Okay. And so what this tells you is that R3 is going to be equal to 0, right? And so if you want to draw an even more, kind of the most simplified circuit for this one, okay, it would look something like this. Okay. And so since surface 3 here is a black body, it's not going to have a gray body resistance. And so you can just kind of get rid of that. Okay. And then from here, what you can just write directly here is going to be sigma T infinity to the 4th. Okay. And so for this problem, you kind of have this kind of modified circuit right here. Okay. And the goal, and remember, the goal for these problems when you have gray body resistance is mostly to solve for these radiosities right here, J1, J2. Okay. Okay. So any questions here on the setup for problem 4? Okay. All right. And so just like I mentioned, the main things that we have to solve for J1 and J2. Okay. Right. And so J1 and J2, the way that we solve for that is we form a linear system of equations using the circuit. And the way that we do that is we take our J1 and J2 nodes, and then we sum up all the heats going into and out of those nodes. Okay. All right, and so I'll give you an example with, let's do the J1 node right here, okay? All right, and so for J1, what we have is kind of we have one thing coming in, okay? And so we have one thing coming in from this resistor, okay? And we have two things going out, right? Right. So the way that we do this is we make an equivalence, okay? So we say that all the heat's coming in has to equal all the heat's coming out, okay? All right, so let's do the heat going in first. And so going in, what we have is this heat transfer between node 1 and node J1, okay? And so remember, the way that we compute the heat transfer over resistors, we take the difference in the nodal values, and so we take sigma T1 to the fourth, okay? And we minus J1, and then we divide it by the resistance in between them, which is just R1, okay? Okay. And then coming out, we do the same thing, but for both of these arrows, okay? And so for one arrow, we're gonna have one that goes between J1 and J2, okay? And so we have J1 minus J2 divided by R12, okay, plus. Then we have the heat transfer going from node J1 up to node 3, okay? And so this is J1 minus sigma T infinity to the fourth, all divided by R13. Okay. And then from here, you would plug in all the numbers, and you would get a numerical, equation for J1. Okay. And you would do the exact same thing for the J2 node. Okay. And so you get two equations, and then from those you can solve for the unknown J1 and J2. Okay. All right. And so, I'll let you guys take it from here on problem 4. But are there any questions, any other questions on the last two examples? Okay. All right. And so that's everything I want to say about radiation exchange. And so hopefully that helps you guys out with the homework and helps you guys understand these concepts a bit more. Okay. And so let's go over some of the learning objectives for radiation. Okay. And so I don't think we'll have time to cover all of them because we have about 25 minutes left in the class, but I'll go over some of the more important ones. Okay. Okay. All right, and so let's start with the very first one, because the very first one I think is one of the most important ones, okay? And so the first learning objective for radiation is to explain the physical mechanism behind radiation heat transfer and compare it to conduction and convection. Okay. All right, and so this is, I think this is probably the most kind of significant learning objective for radiation, because the way radiation occurs is very different compared to, compared to all the other ones, okay? All right, and so the primary physical mechanism, or the way that radiation heat transfer occurs, is through electromagnetic waves. Okay. And so, what's unique about this is that it doesn't use any kind of matter or any kind of medium to transfer the energy. Okay. And so this is significant because this is the way that heat can move through space, right? So if you think about the way that the sun heats the earth, right? There's no matter in between the earth and the sun. And so the only way for that energy from the sun to reach the earth is through radiation, okay? And so that's different from conduction and convection, because conduction and convection relies on matter in order to transfer that energy, okay? As we think back kind of way beginning, when we first started this class, we talked about conduction as kind of the transfer of energy between adjacent molecules, right? And so the way conduction basically works is that you have one molecule with a certain amount of heat and it's kind of vibrating really quickly because it's really hot, okay? Then that molecule is going to transfer that heat, some of that heat, to the next neighboring molecule, which is going to transfer that over and over and over again, okay? And so both conduction and convection rely on that, rely on molecules and matter in order to transfer heat, but radiation does not. And so that's something that's really important with radiation. And so that's probably its biggest distinguishing characteristic, okay? And that's partially why it makes it so difficult to study, especially, even within a heat transfer class, because, even, a lot of the physical mechanisms that it uses, is probably, you would probably better learn that in like an optics class or like a laser, maybe a laser tech class, right? And so it's very different than, what we, how we study other forms of heat transfer, okay? All right, any questions on this? Okay. All right, and so now let's do learning objective 2, because that one has a lot of good definitions, okay? All right, and so in learning objective 2, we're going to define emissivity, absorptivity, reflectivity, and transmittance. Okay? Okay. All right, and so all of these are kind of really important terms, that you should know, and just know that all of these are properties of a certain surface. Okay. And what these do is that they define or they specify how well that surface is at either emitting radiation or taking it in. All right, and so let's go one by one through each of these properties here and define what they mean. So let's start with emissivity. So this is probably the one you'll see most common, especially in your, in your radiation problem solving. Okay? And so emissivity has a symbol of epsilon, right? And so what this tells you is how well or how efficiently that surface emits radiation. And just like the rest of these properties, this can be a number between 0 and 1. Okay. Okay. Where in emissivity of 1, what that tells you is that you have maximum efficient radiation emission. Okay. Okay. And usually an emissivity of 1 is usually only reserved for a special type of surface, which is called a black body. Because remember, black bodies are kind of, you know, theoretical kind of approximations that we can use for the surfaces. You know, but in reality, that's usually kind of hard to achieve. Okay? And so so on the other side of the spectrum, an emissivity of 0, what that tells you that the surface cannot emit any radiation. Okay, which again is also you know, not impossible, but extremely difficult to do in practice. And so you have to be pretty deliberate and treat your surface well. Right? Actually, no, I will say that it is impossible, because as long as the surface has some kind of heat, no matter what you do to the surface, it's going to radiate some heat. Okay, and so your emissivity is always going to be something in between these two extremes. Okay. All right. Next, we have absorptivity. Okay. And ooh, I think this absorptivity has a symbol of alpha. Okay. Right. And so absorptivity it reflects how well the surface is at absorbing radiation. Okay. Right. And so, you know, whenever radiation hits a surface, you know, a lot of it can be absorbed, right? And so what absorption basically means is that the surface, you know, took in the radiation and then it took in that thermal energy in for itself. Okay. And so absorption is kind of what you would expect is, you know, if you wanted a surface to be heated up through radiation, okay, it would need to be able to absorb it. Okay. And so absorption basically means that the radiation hits it and it just stays on that surface. Okay? And so kind of visually it looks something like this. We have your surface, you have radiation coming in, okay? It hits the surface and then it stays. Okay? And so when it stays, it usually goes into increasing the temperature or increasing the thermal energy of that surface. Okay. Any questions on this so far? Okay. All right. Next is reflectivity. Okay. And so for reflectivity is the symbol of rho. Okay. And this expresses how well the surface is at reflecting radiation. And so this is something that's unique to radiation too. And so, you know, if something radiates on a surface, the surface can, you know, depending on the surface, it can just say, no, I don't want any of that, right? And so visually it looks something like this, right? So you have radiation coming in, okay? And if it reflects, you know, it's just going to bounce right off, okay? And then go back to where it came from, okay? And so reflection is something that's important because, you know, any radiation that's reflected, none of that is absorbed by the surface, right? And so let's take an extreme case. And so let's take a mirror, for example, okay? And so mirror is known for reflecting light, being a very good reflector of light, okay? If you try to heat that mirror with some kind of radiation, okay? So let's just say, you know, you're trying to heat it up with a laser or something, okay? What's going to happen is that the mirror is not going to heat up at all, right? And so in a perfect, you know, if we're considered like a perfect mirror where it reflects absolutely everything, the laser is going to hit the mirror and it's just going to bounce back to where it came from, okay? And so the mirror itself is not going to change in temperature, but you're probably going to be missing an eye because the laser is going to bounce off and it's probably going to hit you, and you're not going to be a happy camper, okay? And so reflectivity is something that's important because it's you know, anything that's reflected is not absorbed by the material. All right. And so finally, you know, the last thing we have is transmittance. Okay. And so transmittance has a symbol of tau. Okay. And so transmittance expresses how or how well the surface will allow radiation to pass through. Okay. Okay. And so visually it looks like this. So let's say that you have a surface and you have radiation coming in. Okay. If that radiation is going to be transmitted, then it just goes right through. Okay. Right. And so this one's really important because you know, any radiation that's transmitted is also not going to be absorbed. Okay. Right. And so as an example, let's take your window. So window's not the best example because, you know, we all know a window does heat up, right? And so if you keep your car window out in the sun, it heats up to a certain degree. Okay. And so a window doesn't have perfect transmittance. And so there it has some it does absorb some of the heat. Okay. But, you know, if you had a perfect window and let's say that it had perfect transmittance, okay, and so it let basically 100% of the radiation waves pass through. And so in that case, you know, the window's not going to heat up because all of the radiation that hits it is just going to pass right on through and none of it's going to be absorbed by that material. Okay. And so these are all very important properties, especially if you're going to be working on systems where you know radiation is going to have a big effect, right? And so if you can know these quantities, that's going to tell you a lot about how well your surface is going to react thermally with, you know, the other surfaces in the model. Okay. All right. So any questions on this?
What are those like reflectivity and transmittance? Like I would think like a black body has like 0 reflectivity and then 0 as
yes.
well.
Yeah. So black body is going to have 0 reflectivity and 0 transmittance because for a black body, the absorptivity is going to be 1.
Okay.
Yeah. Actually, that's a good point. I should bring that up. And so, you know, the absorptivity, the reflectivity, and transmittance, they're all related to each other. And so if you add all of them up, and so you do alpha plus rho plus tau, okay, they all have to equal to 1, okay? Because all of them are essentially fractions. And so they express a fraction of how well, you know, the radiation either gets absorbed, either flex or transmittance, right? And so, you know, the radiation, you know, it has to do always one of those 3 things. And so, you know, their sum always has to equal to 1. Okay. Any other questions on this stuff here? Okay. All right. And so I'm going to skip down a little bit, right? And so let's talk about learning objective 6, right? Because this one is pretty important. And so let's talk about view factor. Okay. All right. And so for view factor, you know, this is something that, you know, we've been using in our radiation exchange problems. These express how well or how much of the radiation from one surface hits another surface. Okay. Right, and so our view factors are always given, you know, they have the symbol capital F, okay? And if you notice in our view factors, they always have 2 numbers or 2 entries in the subscripts, okay? And so the most generic one is going to be Fij, okay? And so what this expresses is, so let's say that we have some surface I right here, okay? And we have some surface J, okay? Right? And so surface I right here is going to be radiating all throughout, okay? Right? And so surface J is going to catch, it's going to catch some of this radiation, okay? But it's not going to catch all of it. And so it's only going to catch a small portion of it because it's only a small surface, okay? And so Fij right here, this is the percentage, or this is the fraction of the radiation that leaves surface I that hits onto surface J, okay? And so this Fij, again, this is a fraction, okay? Okay. And the lowest value you can have is 0, and so what that tells you is that none of the radiation hits the surface, okay? And so the other extreme is 1, okay? And so a view factor of 1 means that all of the radiation that leaves one surface is going to hit a different one, okay? All right. And so the way that we compute these is we kind of have several different approaches. And I think this is kind of where a lot of the creativity and radiation problem occurs, okay? And so the first way that you can compute this is through a table, okay? And in particular 12.2. And so table 12.2 will give you a list of formulas that you can use to compute these view factors for certain situations. Okay. And then the other ways that you can compute this is through our view factor rules, okay? And so we already saw both of those in our example earlier today. And so I'm not going to go over them again, but I will give you their names, okay? And so the first rule that we have is the reciprocal rule. And so the other rule that we have is the summation rule, okay? Right. And so usually, you know, for any kind of radiation exchange problems, you're going to use a combination of all of these methods here in order to solve for your view factors. Okay. And so for the exam, but for the exam, you know, what I'll probably do is I'll probably, you know, eliminate the need to look up any formulas in a table. Okay. And so, you know, if, you know, for the radiation exchange problem on the exam, I'll give you a formula that will help you kind of get started with the problem. Okay, so the formula will probably allow you to compute the view factor between two surfaces in the problem, but you're going to need to apply the other view factor rules in order to find the other view factors. Okay, and so don't worry about having to hunt through, you know, a table to find the formulas, but you should know how to apply the rules in order to find the other ones. Okay. All right. Any final questions on this? Okay. All right. And so, you know, before we end for today, so this is our last lecture class together. So I just want to take a moment and just say thank you guys for making this class a great class, right? And so, you know, I know this semester just, you know, I mean, just to put it lightly, you know, this semester sucked, right? So we had to take it all virtually. You know, you had to put school into your homes and to, you know, take all the exams virtually, right? Interaction with each other and with me has been tough. And you know, but I'll say proudly that all of you guys toughed it out, right? So all of you guys put in a ton of work into this class. You know, I'm really proud of everything that you guys done, and I just want to say I really appreciate, you know, all the work that you guys did. Okay, because it's one thing to teach a class, but you know, it's nothing without, you know, buy-in from the students. And you know, I'm very thankful and I'm very grateful for all that you guys have done to buy into, you know, what we've been doing and to you know, and to put all the work in the class. And so, you know, I really enjoyed our time together. You know, I know probably you guys are feeling not so great because the final is next week, but just want to say thank you. And, you know, for those of you guys who are graduating, you know, I want to say congratulations. You know, you guys made it. It's, you know, this probably been the, you know, the hardest college journey that you can have in this pandemic like this, but, you know, you guys did it and you guys conquered it. And so you guys deserve all the respect and all the love in the world. So, you know, you know, for those of you who are graduating and, you know, for those of you who are not, you know, if I can be a resource for you guys in the future, you know, write reference letters or, you know, you want my feedback on any kind of work that you're doing, I'm always going to be there. And so you guys will have my email forever. And so, don't be afraid to reach out, right? And so if I don't see you next week, if you want to take the exam in peace, then, I just want to say, have a great summer. I really enjoyed our time together, and, I'll see you when I see you.
Thank you, Professor.
All right. Thanks, guys.
Thank you, Professor.
Right.
I had a quick question. This lecture is still going to be posted, right?
Yes. It's recording. And so I'm going to post it, this afternoon.
Awesome. All right. Thanks, Professor. Have a good summer.
Thanks. You too.